And good afternoon to Dr. Zamir and my fellow friends. Today, our group will present about organic solar cell. Uh, Next slide. Okay. I will present about the introduction of organic solar cell. Mushfiq. No, okay. Okay, I will present about the introduction of organic solar cell. For device configuration part, we'll talk by Shreyas. Sri Izyani and Mushfiq will present on operating principle, and for application part, we'll present by Rajat. For introduction part, firstly, I will talk about the background of organic photovoltaic. After that, I will introduce the organic solar cell. Then lastly, the type of organic solar cell. Early research on the electrical behavior of organic material was common in the 1960s. Photoconductive organic material was then discovered in the 1970s. However, only after the announcement of conductive polymer in the late 1970s and of conjugated semiconductor and for emission polymers in the 1980s, a new impulse and interest in the field was generated. Nowadays, electronic based on organic compound has developed such that it can be considered a valid replacement to the conventional one. Solar cells have been widely considered as a next generation clean and renewable energy resources. The majority of photovoltaic were silicon-based conventional devices. In the last decade, the dominance of this traditional solar cell is being challenged by the emergence of their generation photovoltaic technologies. Research led to the production of organic solar cell. There are third generation of solar cell technology and also known as organic photovoltaic cell. Okay. These organic cells are incredibly powerful when it comes to absorbing the light from the sun. They are able of sunlight than any other solar cell. This form of solar power will drive the industry forward at rapid speed, especially with new research and development making it possible for them to have increased sustainability. Organic photovoltaic convert solar energy into electrical energy at rates that are far more efficient than any other form of solar cell technology. Even the silicon cell that are found in the majority of solar panels. Prof. Brabeck Working Group has held the world record for efficiency in an organic photovoltaic module of 12.6% since September 2019. The multi-cell module developed at Energy Campus Nuremberg has a surface area of 26 cm square. In February 2021, National Renewable Energy Laboratory research scientist Byron Lyson, as part of an international research team, has achieved a record-breaking 18.07 power conversion efficiency from an organic photovoltaic solar cell. Next slide. Okay, what is organic solar cell? The first organic solar cell was fabricated by Kelvin in 1958. It consists of thin layer of organic semiconducting material, hence the name organic solar cell. An organic solar cell, also known as plastic solar cell, is a type of polymer solar cell that utilize organic electron. These are a branch of electronic that deal with conductive organic polymers or small organic modules in order for light absorption to take place as well as charge transport. This is so that electricity can be produced from sunlight via the photovoltaic effect. The molecule used in organic solar cell are solution processable at height. The secret coefficient of organic molecule is high, so large amount of light can be absorbed with a small amount of materials, usually on the order of hundreds of nanometers. One of the biggest difference between silicon photovoltaic and organic photovoltaic is in their physical structure. Organic cells are made with compounds that are typically dissolved in ink and printed onto thin plastic, which means that organic solar cell can be flexible and incorporated into more places or structure than crystalline photovoltaic. Okay. I will roughly introduce the different type of organic solar cell and its explanation will be presented by Shreyas. There are three type of organic solar cell. The first one is single layer. It's the simplest one. The second is bilayer, and the last one is butt heterojunction. That's all from me. I will pass it to Shreyas. Thank you.
Hi, can you hear me?
Yes, we can.
Okay, so my name is Shreyas Subramaniam, and first, these are some of the companies involved, right? Next slide, please. Right, so I'm going to be presenting on the device configurations for organic solar cells. So there are three main configurations and other configurations that people are working on. Next slide. So we start off with this single layer organic solar cell. Now, a single layer organic solar cell consists of three parts. First, the top part is made out of material with a high work function. So it's usually ITO, indium tin oxide. It could be any other transparent conducting oxides. And then the second electrode is made out of metal with a low work function. So metals like aluminum, magnesium, and calcium. And sandwiched between these electrodes is our organic semiconductor material. Next slide. So the organic layer is the site for exciton production. When light hits the organic layer, excitons are produced, but without an electric field to separate the exciton, it's just going to recombine and lose its energy to the organic layer. It's just going to become useless heat. So what we need is an electric field. This electric field is produced by the electrodes, which have different work functions. So this splits up the exciton into electrons and holes, which the hole is then attracted to electrode 1, the one with the high work function, and the electron is attracted to electrode 2, the one with the low work function. Now the achieved power conversion efficiency of these kind of cells are less than 0.1%. They're not very efficient, they're not very good. And the problem with this is the electric field is not strong enough to effectively split the excitons. Next slide. So as an improvement to our single layer organic solar cell, we have a bilayer organic solar cell. Instead of one layer, we use 2 layers of organic material, an electron donor material and an electron acceptor material. So the electron donor material has a low electron affinity and the electron acceptor material has a high electron affinity, and 2 different type of semiconductors. Right, next slide. So in between the 2 layers, an electric field is produced in the interface. And this, at this interface, excitons are split. The strong electric field produced will split up excitons very effectively. The problem, but of course, this layer is only capable of achieving an efficiency of about 1%. And the problem with this is the excitons have to travel too far to get to the interface point. And the reason is for the layers to effectively absorb light, they need to be at least around 100 nanometers. But the diffusion length, how far the exciton can travel without recombining, is around 10 nanometers. So only some excitons can reach the interface, and that means it's less efficient than what we want it to be. Right. Next slide. So to improve on this, we have a bulk heterojunction, also called a dispersed heterojunction configuration. Next slide. So in the organic layer, the electron donor and electron acceptor materials are combined together in a way, it's a nanoscale blend of material. It's been described like a comb-like configuration, right? So then the excitons have to travel a shorter distance to be able to reach an interface, and thus it's more efficient. So nowadays, most of the research in this field is focusing on this bulk heterojunction, and this is what is being proposed to actually make commercially viable solar cells, organic solar cells. So right now, as Nabila mentioned just now, the current record is 18.07%. The link is here to that article, and they use 4 materials in the bulk. Right. Next slide. So, okay, most of these other configurations are theoretical or just for research purposes. Some are being proposed as an improvement to bulk heterojunctions. So we have discrete heterojunctions. It's basically the same as the bilayer configuration we saw just now, but instead of 2 layers, you can just have more layers of the semiconductor material. Then you have graded heterojunction, where the donor and acceptor layers combine such that the gradient is gradual. So yeah, then a continuous heterojunction, basically the same idea. It's a different way of manufacturing. And then laminated layer devices, where you have a donor layer and an acceptor layer, and in between you have the dispersed or bulk heterojunction sandwiched between the 2 layers. Right. I think that's it for my part. Right. Thank you.
Okay, who's next?
Okay. Hi everyone, I'm Sri Iziani, and now I will explain about how organic photovoltaic works. Okay, next slide. Next. Organic photovoltaic cells operate in different manner from inorganic solar cells. As we are known, inorganic solar cells are made of silicon, and organic solar cells are made of plastic polymers and other flexible materials. In organic semiconductor, the attraction force between the photo-generated electrons and holes are very high. Unlike inorganic semiconductor, the absorption of photons will generate free electrons and holes. So, to produce and transport free carriers throughout the organic device, the excitants must be dissociated. Next. So, the free carriers for organic device can be generated by creating heterojunction between two dissimilar materials, a conjugate polymer as an electron donor and fullerene derivatives as an electron acceptor, which have high ionization potential and high electron affinity respectively. There are two molecular orbitals in the organic semiconductor, which is highest occupied molecular orbital, HOMO, and the lowest unoccupied molecular orbital, LUMO. The band gap between HOMO and LUMO is called as band gap for the organic semiconductor materials. Next. Now we will go in details how inorganic solar cell operates. For an inorganic solar cell, when photons from sun hit the cell, they are absorbed and create electron hole pairs. The electrons and hole are attracted to electrodes and opposite surfaces of the semiconductor, creating a potential difference and electricity can be generated. Now we will go how organic solar cell operates. When the cell absorbs light, the electron and hole immediately form a bonded pair, which called as excitants. The excitants that are formed in donor materials can be dissociated at donor-acceptor interface. Once separated, the electron can be transferred to the acceptor of the material and can be transported to the cathode of charge collection. The hole created in the donor material travels throughout the material, collect at the anode. In general, a successful organic photovoltaic cell requires 4 important processes, and this will be explained by Mushfiq.
Thank you, Doctor. Welcome everyone to my part of the presentation. I'll be just principally discussing about how the photons hit on organic solar cells and how the electricity is generated. There are principally 4 steps. Number 1 step being the light absorption, second one being the excitation diffusion, then the third one the exciton dissociation, the fourth one is charge migration and collection. The first one is as simple as the name says, the light absorption. Usually the solar radiations that hit the solar cells, and actually it gets converted into excitons. So the most efficient organic solar cells has a band gap of around 1.5 electron volt, which is near infrared and red region of the electromagnetic spectrum. And incoming photons actually get absorbed by the crystalline silicon, which takes the atom that absorbed the photon into an excited state, and it in turn creates an exciton, and which we're going to discuss in the next slide. But we must remember one very important thing. For like my previous speaker said, that in organic solar cells, the created exciton is strongly bound, unlike the inorganic solar cells. So we must ask ourselves, what is exciton? Exciton is simply a bound state of an electron and a hole. That is actually a quasi-particle, which means that it actually created by the interaction in the microscopic level of the materials, and the lifetime of this exciton are usually very, very short. And these, as we already discussed, that this is a bound state of an electron and a hole, so these are electrically neutral in nature. So to create electricity, we must separate them. That means that to create electricity, we must take the exciton and we divide that into a hole and an electron. So how to do that? So first we must understand about exciton diffusion. Exciton diffusion is nothing but the spreading of exciton throughout the semiconductor. As we already discussed, that the created excitons usually have a velocity and also last for a very certain amount of time, which is very small usually. So it actually travels through the semiconductor, and this distance which the exciton usually travels is called the diffusion length. And And we must remember one more important factor about the organic solar cells. That is that organic solar cells comes with an electron donor component and an electron acceptor component, and the region between these two components is called the interface, only where an exciton can be decoupled. Like my previous speaker said, there is an electric field that actually decouples the exciton. So as a result, the distance between the exciton and the interface must be very, very short, so that the disassociation can take place. That is why the third material from the single layer and bilayer, the third material, the bulk heterojunction one, is the way more efficient, because the distance between the exciton and the interface is very, very short. But it creates a own set of problems, because making the distance shorter, we must make the organic solar cell field very, very thin. Making it thin creates its own sets of problems. That means that it becomes very inefficient in absorbing the incoming photons, all the radiations that is hitting the solar cells. So to make it very efficient in absorbing the incoming photons, we must make it thicker. So now we are finding two problems that are counter to each other. We must make the solar cells, the solar layers, especially the organic solar cell layers, thick, to make it very efficient at absorbing photons, and we also must make it thin, so that it can be very efficiently dissociate these excitons. So we must strike a balance, that we make a sufficiently thick solar layer that can actually absorb sufficient amount of incoming photons, and at the same time we make it thin, so that it can actually the dissociation of the exciton can take place. Now we are going to move into the dissociation part itself. The dissociation is nothing but actually the transfer of an electron to the acceptor level, and which in turn creates a hole in the donor component, thus creating what we call a charge transfer state, CT. And the charges move away, usually the charges move away from each other. But we must maintain this charge separation, because if we let the hole and electron recombine, then there will be no electricity generation. So the charge separation is very important. So in a nutshell, to create current in organic solar cells, charge transfer and the charge separation both need to be always maintained. Now we are going to discuss about the charge migration and the collection. To create a current, as we discussed, the electron and the hole must maintain the charge separation and move away from the interface. And eventually they should reach their respective electrode. For the electron, it should be anode, and for the hole, that should be cathode. But how efficiently this transfer process occurs, it depends on the structure of the crystal itself. If the material has a very good order, that means the crystal structure is very orderly, then the charge mobility will be very, very high. If the charge mobility is very high, then the faster the electrons and hole can move away from each other, and that in turn that can create more current, which in turn makes the organic solar cell way more efficient. Thank you. That is the end of my presentation. Thank you.
Assalamu alaikum and good afternoon. Hope you are hearing my voice clearly.
Yes, okay.
Yes. Before we go into applications, I want to discuss some advantages and disadvantages. Some of the advantages of organic solar cell is the lightweight. They are also thin and flexible. They weigh around 500 per square meter. They are 40 times lighter than the silicon solar cell, and also can be printed into a thin plastics, which make it so thin. They are vary in transparency, colors, and shapes. Organic solar cell can be semi-transparent and also can be in any color and any shape. They are easy to integrate with other products, since they are it can be transparent, and so they can be designed as needed. The short energy payback time generates as much energy as it's consumed during production. There are low environmental impact during manufacturing. less energy consumed than organic solar cell. About the advantages, we have the biggest two disadvantages here, low efficiency and short lifetime. As mentioned, the greatest efficiency recorded for organic solar cell is 18%. So it's compared with other solar cells, it's considered low. And also the lifetime. The lifetime of organic solar cell, they last for less than 20 years. The third disadvantage is the cost. The cost actually it's not we can in the future it would not be a big disadvantage. It will be advantages because it's low manufacturing cost. But currently, because this is still new industry, so of course the prices will be higher. So those limitations, it's limit the application of the organic solar cell. Now we come to the applications. Next slide. The organic solar cell is just as the traditional silicon solar cell. They turns the sun energy into usable electricity. So they could be used in the same way. But the unique thing about organic solar cell, they are more adaptable than the traditional ones. But because of the disadvantages, because of the lifetime and the efficiency, the application of organic solar cell currently limited. But we can use them where crystalline silicon and other inorganic solar cell technology cannot be used. There are two main fields where we can use the organic solar cell because of their advantages. So next slide. I want to talk about two fields. First, the architecture. Organic solar cell is used on the roofs and walls of the building, which are not designed to carry larger loads such as storage buildings. Those buildings are not designed to carry much weight on their roofs or in the walls. So the organic solar cell is the most suitable to reduce the energy in such buildings. They are very simple fixation. So simply, organic solar cell is just can be. We can use a double-side sticky tape to fix them on building or. They are excellent candidate of building integrated semi-transparent photovoltaic cells, since it is achieves semi-transparency with responsible uses compared to non-transparent cells and color natural absorption. So because are they semi-transparent, they can be used in windows, in any base or any part of the building. We want it to be semi-transparent. Here are two examples. This is a street furniture in King Abdullah University. This was installed in 2020. And here is one of the oldest building uses the organic solar cell. It's solar trees. It's in Germany. As we can see, this building is not designed to carry too much weight. And here, if you can see, there is in the above something like the point. It's not really clear, but we can see that those are the organic solar cell used in this building. The next region to use the organic solar cell is the wearable uses. They are so flexible, so they can be used in clothing, bags, or also camping products. As we can see here, this beach bag, so it's the design is very nice, and everyone, I mean, not everyone is girls bag, so you can easily take it, go to the beach, and very nice design, and you can generate the power. You can charge your phone or use it for whatever you need the electricity for. And here is one backpack. So yes, you can. It will not add too much weight to your bag. When we go to camp or in everyday bags, we don't like them to be very heavy. So this technology is very nice to be used in the bags or in clothing. Next. Yes, the technology of organic solar cells is continuing to improve, and hopefully in the future we will see more and more application in a wider scope of the market. So some of application that we may see soon, the remote lighting systems, the transparent in cars, maybe motorbike, and they are also can be used for portable power supplies, satellites, solar electric fences, toys, watch, and calculators, and also solar panel poster. That's all for my part, and for my team, we can go to question and answer session. Thank you.
All right, thank you, group number 8. So let's continue with Q&A session. Any questions from the floor?
Doctor, I have questions.
Okay, go ahead.
What is the commonly material used in the organic solar cell, and how and what is the form of the organic solar cell? Is it solid or liquid or other? Thank you.
All right. So what's the common material used in the organic solar cell, and what's the form of the material?
Should I take this?
Yeah, go ahead.
Yeah, go ahead.
Okay, so as far as your second question, it's a solid, and your the first question, it's still very theoretical, and there isn't a general formula for making for the materials, but some of the materials use fullerene blends and various other plastics and organic polymers that they're too long for me to remember the names or really know what they are.
Okay. Anyone else would like to add on that, or? Okay.
Oh, also one more thing. In the ITO, instead of the ITO, I think things like PDOT and PDOT PSS, I'm not sure what that stands for, but it has the same properties as ITO. But if you embed silver nanowires or carbon nanotubes inside it, it's more conductive, and it's being used in conjunction with ITO or as a replacement for ITO, I think. Right.
All right. Okay. So next question. Any more questions? Right, maybe one question. What are the main issues with organic solar cells that are hindering them to be widely deployed?
Should I go for that?
Yep, go ahead.
Yep, there are a few reasons that are holding back these organic solar cells. Number one of being then they have a very the excitons have a very high very high binding energy, so it takes a lot of energy, electric field to just to separate them. So it actually and also there is another factor that we discussed here, that the distance between the exciton and the interface, it must be very short, right? So if we make it too short, then the photon absorption becomes too low. So these are counter intuitive problems. So that's why these are one of the problems that is holding back the efficiency level and the large scale deployment of these organic solar cells.
All right, so we have a question here from Hazik. How to know organic solar cell has deteriorated?
There's a very the most easy trick to the power output will be getting lower and lower and lower by the day, and the more time it progresses.
Basically, if it doesn't work, it's not.
Okay, so it doesn't work, or the power deteriorates. So any other questions? Anyone? No more questions, really. So what is the optimum thickness for the polymer in organic solar cells? Or range of optimum thickness?
I'll take this because it's to
Okay.
do with my part. Right. So to absorb light effectively, the thickness of the organic layer should be around 100 nanometers. But well, on this order of magnitude of 100 nanometers, but for the electrons to diffuse, sorry, the excitons to diffuse to the interfaces in the bilayers and the discrete heterojunction, the distance should be very short, around 10 nanometers.
So do you think, do we have a way to increase the diffusion length of the excitons when we have to use thick, like 200, 300 nanometers of the organic layers? Can I do something to improve the diffusion length instead of 10, say 100 or 100 plus, so that they can survive?
Well, maybe something to do with the material, but I'm not sure what.
Sorry, doctor, I'm really sorry. Someone is calling me. I had a parcel to receive. He's calling me so many times. Really sorry, doctor.
Okay, no worries. Okay, just now, one of you mentioned about the order of organic molecules, right? Is it related to the crystallinity or something?
Yes, doctor. I think it is related to the crystallinity because the order of these molecules actually determines how efficient they will be, what will be the distance, and what will be the electric field and strength of this organic solar materials, solar cells.
So in the organic solar cells, do you use what, amorphous or polycrystalline, or is there any other form?
So right.
Well, it's not inorganic. It's organic, but do we have crystallinity in organic polymer?
Yeah, of course we do, doctor, because we're using silicon crystalline. So of course we because there is a layer of organic material on top of that. That's it, doctor. So we have crystallinity, yes.
So is it polycrystalline then?
That's not what I'm saying.
Right, try to search on that, okay? Try to search whether or not we have crystallinity for organic molecules.
Okay.
And what sort of crystallinity do we use in our organic solar cells? Right. Okay. Any other questions, guys?
Yeah.
Anyone with questions? All right. My perhaps last question, or second last. Can we use organic solar cells indoor? Inside our house, inside our room? Can we? What do you think?
I can take this. Yes, we can actually. There are
Alright,
some
okay.
researchers, and hopefully soon we can see those devices in our homes.
Okay, so what do you think it takes for us to use solar cells indoor? Because when you talk about solar cells, um, it's synonym. It is synonym to outdoor use, right? And we are talking about harvesting the sun, the power from the sun, and bringing the cells indoor means you don't have the sun inside the building. So how does it make sense then to use indoor?
We actually we still have some sun coming to our.
Well, for example, if you completely have if you completely close your curtain and you don't have sun coming inside and you just have you know whatever sources of light inside the building, do you think we can harvest using your solar cells?
Doctor, we think we can because it is a near infrared and red region. So it depends what kind of light actually penetrates because red light actually travels the farthest. So I think, yeah, we can do, but the intensity will be very low.
Can you harvest from your indoor light then?
Indoor light, doctor, depends on the light we're using, right, doctor? If it is a fluorescent light,
Say white LEDs.
white LEDs,
Down light white LEDs, for example.
yeah, we can do because white LED is mixture of all the lights, right? So there is a certain fraction that is actually carrying red light, right? And these organic materials are usually sensitive to near infrared to red light. So yeah, but the efficiency will not be that high because the white light is not, and of course our lights inside the room is not that powerful.
All this
It's
depends on the material. All this
Okay,
depends
yeah.
on the material we use, right? Depends
Okay.
on which frequency spectrum it can absorb and its optimum for.
So okay, we learned before to be able to achieve a high conversion efficiency for sun harvesting outdoor, we are talking about a band gap of about 1.5 so that you have the peak, right? You hit the peak. So do you think the peak will maintain, or the peak of the band gap or the optimum band gap will maintain indoor? What do you think? Just a random question.
Uh, I
Because
don't think so.
Shreyas mentioned about spectrum and then the dependency on the wavelength and everything. So Shreyas, do you think you're gonna have to tune the band gap for you to use indoor for organic solar cells? What do you think?
So,
Yes.
doctor, you're
Yeah.
asking me, Mushfiq.
Okay. Shreyas go first, and then Mushfiq.
Okay. Yeah.
What do you think, Shreyas? You unmute. You need to unmute first.
Oh, sorry. I think
go
it's
ahead.
quite different, the spectrum between the outside spectrum and the indoor spectrum.
All right. So how different? Do you think you're gonna go for higher or lower band gap optimum indoor? What do you think? Looking at the light outside and looking back at your door, at your lights inside. But do you have to use higher band gap for indoor harvesting or lower band gap for indoor harvesting?
I think lower band gap.
Lower?
Yeah.
So that means lower than 1. Okay, outside we're talking about 1.5 being the optimum. So we are talking about 1.1, 1.2, is it?
Yeah. Probably.
Okay. How about what makes the light indoor? What makes the indoor light? What makes the white light? How about the band gap of the white light in comparison to the outdoor? I think we discussed last time when we talked about, I think, laser diodes or LEDs, where we talk about the component of white light. I think last week or so. So you remember the peak of the white light spectrum? For others as well.
Yes.
For others as well. If you remember, just write it down in the chat box. This is a discussion.
Doctor, can I try?
Yeah, go ahead.
Yeah, Doctor, because our indoor lights, especially the LED lights, these are a combination of three lights, that is RGB, red, green, and blue, right, Doctor? So the red is actually very close to the 1.5. It is roughly 1.59 electron volt, the lowest of it. So it can, our organic solar cells, that the most efficient one, which borders around 1.5 electron EV. So it is near infrared to almost to the red. So I don't think it will not be that efficient in under a LED light, because LED lights are specifically designed to emit the very specific frequency. This is red, green, and blue. So I don't think it will be that efficient. We must need to increase the band gap to be efficient in indoor.
All right. So you said we must increase the band gap to how much? What do you think?
Doctor, I will say. Just I have to look at the table though. So the table says that, Doctor, for the blue we need to go around 2.85 to 2.48, and for the green one to 2.38 to 2.1. Then I will go for something like 2.4, 2.2, 2.3.
Okay. So if you want to do indoor PV, indoor photovoltaic, which is a relatively new area of research.
Yes,
so the optimum band gap of the solar cell, whatever solar cell they want to use, the solar cells need to have a band gap of about 1.9 to 2.0 electron volt.
All right.
In order to align the devices to the, say, my white light.
Yes,
so I need to use something like amorphous silicon 1.8 or your organic with a bit tuning to get to close to 2 perhaps. Or you can even use perovskite. You can also use well, those are the main three ones. Well, you can also go for gallium arsenide with a bit of tuning. But silicon on the other hand will perform very poorly. Silicon, by silicon I mean crystalline silicon 1.1 will perform very poorly indoor because of the spectrum mismatch.
Mismatch. All right.
Silicon will perform great in outdoor environment because the outdoor peak is at about 1.4, 1.5, and silicon is 1.1. But the moment you bring silicon indoor to 1.9 to 2.0, silicon is like 1.1 down there, and your optimum band gap for indoor is 1.9 to 2.0. And silicon, to give some perspective, if the silicon in solar cell performs with efficiency of about 20% outdoor, the very same cell will perform under 5% indoor.
Yeah, understandable.
So yeah, due to the spectrum mismatch. So the answer to that will be about 1.9 to 1.0. So you would have to tune the band gap of the indoor solar cells based on whatever relevant materials to around 1.9 to 2.0.
Okay, Doctor. Okay, Doctor.
So indoor light frequencies are higher than outdoor light frequencies?
Yes.
Well, if you talk about indoor, to go to the details, indoor has a very narrow spectrum. Okay, so we'll be discussing about 450, 550 peak, 2 peaks for the white light. But on the other hand, outdoor, the spectrum is more distributed. So you have UV, you have visible, you have IR as well. But when you do the calculation based on Shockley-Queisser limit, you can search on SQ limit after this, Shockley-Queisser limit. The optimum conversion requires a band gap of about 1.4 to 1.5 in order to perform outdoor. The very same case of calculation, if you do for indoor, it requires about 1.9 to 2.0. Okay, so this is a very interesting finding because based on the calculation, if you go for outdoor PV harvesting, we are talking about theoretical limit of about 33% for 1.4 electron volt. For example, gallium arsenide. So the maximum it can hit is only about 33% maximum with a single junction architecture. So that means P-type or N-type gallium arsenide based solar cell, the maximum it can go is like 33% and no above, no higher than that. On the other hand, if you do the very same calculation based on the Shockley-Queisser limit, if you check in the recent, maybe I can forward into the group later on, the theoretical limit for indoor light conversion can go up to 60%. So that means with the calculation theoretical limit, if you tune your organic solar cells or amorphous solar cell or perovskite solar cell with a band gap of around 1.9 to 2.0, they can even hit up to 57%, 58%, up to 60% of theoretical limit. But at the moment, they are only performing like 9% or 20+%. Some even. The recent one I read from a review paper, perovskite or amorphous silicon has hit up to about 30+% of conversion efficiency for indoor harvesting. So indoor is a very new thing, relatively new. I think it's only being researched for the past 5 years or so. And the reason for that is due to the expansion of the IoTs indoor. So we want everything to be smart, right? We want smart homes, smart TV, smart watches, smart devices indoor. You want to control everything nowadays. And the good thing about that is when we talk about indoor, we are talking about low power devices like smart watches, smart everything, whatever. They are generally low power in comparison to the rooftop PV. And when you're talking about low power, you don't need as much energy from the supplying device, like in this case, indoor solar cells. So the solar cells do not need to produce so much power in order to power the indoor devices. So you only need like a range of a nanowatt up to watt in order to power indoor devices. And this is a very good avenue or promising avenue for the low power devices tuned to indoor PV harvesting to come in and, you know, make the money, right? So, well, I can forward to you a paper from MIT, I think 2 years ago, published on indoor energy harvesting, indoor PV harvesting for IoT ecosystems. And it's very interesting because it's a very niche application. You don't have to talk about megawatt or kilowatt or gigawatt outside. You just have to talk about nanowatt to milliwatt. And you don't need to bring your panels, silicon panels inside because they are performing poorly anyway. And this job can be done by the low power solar cell, like organic or MOSFETs, that has been there traditionally serving niche markets like our calculators or watches. But they're gonna make a big business, billions of business in the next few years for IoTs particularly. Right. So it's very interesting development in the recent years with regard to the thin film solar cells or emerging solar cells like the organic solar cells. So Hifzan, you're close, 2.2 electron volt. So the optimum one is about 1.9 to 2.0. So you're close. Right, any last question to the team? Nope, all good. All right then, let's give our hands to group number 8, organic solar cells. Right then guys, so good job. You have done a lot. You have presented great for the last all the last 8 groups. So well, obviously there are things to learn as well, and I believe you have learned a lot as well in this presentation session, in this assignment. So maybe you can share what did you learn mainly for the presentation. All the groups, all students. Anyone would like to share something before we finish the class in like 2-3 minutes? What are the top 3 things that you learned for this group presentation? If you can name top 3, for example, anyone, not only for group number 8. Top 3 interview question.
Well,
Yeah,
I just learned a little bit about indoor solar cells.
All right, indoor solar cells, good, right? Others? Hazik? It doesn't have to be on the technical side only. What other things did you learn in terms of theme, arrangement and stuff? You know, literature, search, organizing information and stuff like that. What did you find the most top 3, like top 3 things you learned from this presentation? This is going to be the very question asked to you for your interview later on. This is the typical question I asked for the new hires when I did the hiring last time. 3 things. Okay.
I want to talk about one thing.
Okay.
Because this is a new technology, so online we find a lot of information and so much old articles. So the first step when you do your first searches, so you will find some information like some articles will mention that organic solar cell efficiency is only 5% or something like that. So we need to do more and more and more and search for the most recent ones to be very acute about our information.
Yeah. So when you go online, you will typically be overwhelmed with the information, right? So many things to read, so many things to refer. You don't know which one comes first, which one comes later, which one replaces which one. And you have tons of different information to process and organize, right? So that's one, organizing information, I would say. What else?
Using Wikipedia as a guide for further research,
Exactly.
because you can just look up the references in Wikipedia itself, then read more in detail about it.
Exactly. To me, Wiki is the very first gate that you want to go to. It's very fundamental, simple, easy to access, easy to understand before you jump into scientific articles or proceedings and stuff like that. It's a very friendly gate. The first thing to go is Wiki, and then you jump to the specific information that you want to understand further, right? So you know that Wiki is the first gate. Good. Others? Another 1 or 2 points before we finish the class. Working in group virtually, is it easy? You don't get to sit down together and brainstorm, but you just can do online. Did you find that easy? Others as well? Not only group 8. But how about Hazwani? How did you find that, Hazwani? Did you find that easy in comparison to previous year's presentations? Not really. So it's relatively easy. Okay. Anyone found it more difficult compared to sitting down together and chatting, brainstorming? So not really hard, yeah. So group 8, did you find it hard to discuss online or WhatsApp, change information?
Well, I think it's the same as usual, maybe slightly worse, but not really that much different.
Yes,
Okay,
Dr.
so okay, yeah, Mushfiq, okay as well.
Yeah, it's business as usual, Doctor. But the thing is that during the classes we would have met with each other, so we could have asked about the progresses and stuffs. Not anymore, right? Now you have to go through WhatsApp and other stuffs, right? And the thing is that people are busy and stuffs, so it becomes complicated a bit. I'd say.
Yeah, I think most of the what I call the most plausible reason you found it relatively easy because we are now adapted to the new culture. We are now adapted to the new norm. If I probably ask you this question March 2020 last year, right? So we'll probably be everywhere still, still finding how to talk online and stuff like that. But we've been going through this for 1.5 years at least, and we don't know for how long do we have to go like this. Hopefully it gets better very soon. So we are now adapted, I believe, because I found it very hard as well to discuss in schools meeting and to handle classes with students as well. But I found it relatively easier, I believe a lot more easier this year when I compare to last year. So it's not only on you, it's also on me, okay? As a lecturer handling the class. So yeah, we are now adapted. That's good. Okay, let me read some points here. I think this kind of presentation is good. Open our mind to apply what we learn theoretically into the real life. Yeah, that's the most important thing. As what I promised to you, this course is going to connect you the physics with the real life applications. Now, and if you can see outside, I know just now Shrey is looking outside, probably looking into the real life applications and trying to connect to the PN junctions perhaps. Right, Cornelia, being active while in work group, even though it's a bit difficult to communicate during this pandemic, every member is active, giving the insights to the group. Yes, this is what I want you to do. Well, even though I don't have access to your discussion and everything, I want you to be actively involved and participate, because the benefits is not for me, the benefits is for you, right? For other subject may be hard because we need to combine with other schools. Sometimes they not give this much response. Yeah, probably you know your friends already, so it's a lot easier for you to communicate online. Farhan, presentation kind of get easier as most parts of your body is hidden. All right, that's good then. Hidden behind the backstage, so you don't have to practice the body language, which is bad for your skills development. Exactly that, right? So if you are behind the screen, you don't have to practice as much if you compare to the real, say, interview, real presentation, face to face to your stakeholders, lecturers or interviewers, or I don't know, clients or something. It'll be more intriguing. Okay, it'll be more intriguing, but at least you have a you have a time to practice behind the screen, and I believe you have more confidence to be on the screen in comparison to be face to face. Yeah, or not so, or the opposite. What do you feel?
Doctor, I think up till now, I haven't given a presentation live yet in university, actually.
Oh, really? So, in other courses as well?
Well, right now it's my third year. So second year, I don't remember anything that we had to do live, just make videos and stuff like that. And yeah, also first year.
Okay, then
I
that's
don't
good.
remember anything.
So 203 already. Let me finish off. Okay. Yeah. Last year, for this subject, we did online. We did online video. You have to, well, the students had to record a video on the presentation and then post it on eLearn or Padlet. I think last year was Padlet, and then I will then do the assessment online. And I think it's not so real, it's not so real, because you can do multiple times of the recording and you get better over time. But when you do online, you're actually practicing the real online, the real case scenario when you're going to be interviewed for scholarship or for your first job or even for your internship next year. So it feels more live, and yeah, it's live even though I don't get to see you face to face, but it feels more live, and you're present to answer question and to discuss there and then. Okay, so I think it's good for you as well. I think if the situation doesn't get so much better, then probably your interview will also be conducted online as well, because it'll just be sometime in December or January this year, because you're gonna go for your internship in February. So most probably your internship interview will also be online. So this is a good platform for you to prepare for your upcoming, internship or career interview as well. Okay, so we are done with all the 8 groups. So congratulations to all the group for your preparations, for your presentation as well, for your great material as well. So I did not only ask you questions, I also learned a lot for your presentation as well. Okay, so we can explore this further. Done with the presentation. So we're gonna continue with our lecture on MOSFET tomorrow. I'm gonna take perhaps 2 sessions tomorrow and Monday, and hopefully I'll be done by Monday, and then I'll give you some time on Tuesday to do your revision, and we're gonna have our open book test to next Wednesday. So it's gonna cover from PN junction bias until devices. We're gonna have some calculations as well. So it's gonna be a 3-hour open book test from 1 p.m. to 4 p.m. next Wednesday. Okay. So the way we're gonna do it is exactly like the way we did last time, except it's gonna be 3 hours. Okay, so get ready for that. Right then, I'll see you tomorrow. Bye bye. Take care. Assalamualaikum. Stay safe.
Thank you, Dr. Assalamualaikum.
Thank you so much, Victor.
No worries. Bye bye.